Subcommittee on Energy will come to order. Without objection, the chair is authorized to declare recesses of the subcommittee at any time. Welcome to today's hearing entitled Nuclear Energy Innovation and the National Labs. I now recognize myself for 5 minutes for an opening statement. Good morning, and I've already welcomed you to the committee hearing this morning. We appreciate you all being here. Today's hearing will focus on the Department of Energy's National Laboratories research capabilities and the working relationship with the private sector to advance nuclear energy technology, both fission and fusion. The Department of Energy owns 17 national laboratories, 16 of which are operated by contractors as federally funded research and development centers. The government-owned, contractor-operated model allows the labs flexibility to think outside of the box when tackling fundamental scientific challenges. The Department of Energy labs grew out of the Manhattan Project and today provide the critical R&D infrastructure that will enable researchers in academia and the private sector to develop the technologies of tomorrow. It's pretty clear that the challenges in nuclear science can be quite complicated, and we'll hear more about that from our expert witnesses on our panel today. That said, not being a nuclear physicist or anything of that sort, I'm going to do my best to simplify what we intend to discuss in today's hearing. We hope to get a better understanding of what the DO labs do and how their unique research machines and talented group of researchers can enable companies to develop new products. This is especially relevant for nuclear energy R&D, which requires large upfront costs, but may lead to revolutionary technology with long-term rewards. Folks, I would add that the United States has a definite national interest in maintaining our position at the forefront of nuclear technology development. Nuclear energy, as you know, is in a class of its own with the highest energy density of any fuel and yet yields zero emissions, the big goose egg. It is also highly regulated, often a centerpiece of global, especially national politics, and it's associated with the world's strongest economies. In the United States, we invented this technology and we must not forego the opportunity to export more efficient and safer reactor systems that will mitigate proliferation concerns while increasing global stability by providing a reliable energy source. Today, we're going to hear from the president of a charitable organization that has co-invested with the DOE lab to advance a specific nuclear fuel treatment process to convert nuclear waste into a usable fuel. We will also hear from the Argonne National Lab, which invented this fuel treatment process, as well as private companies developing fusion and advanced fission reactors. Needless to say, this is a unique panel of witnesses. I thank the witnesses for participating in today's hearing, and I look forward to their testimony. Mr. Grace from Florida, you're recognized for 5 minutes.
Thank you, Chairman Weber, and for holding this hearing, and thank you to our witnesses for agreeing to participate this morning. For decades, the federal government has provided critical support for energy research and development. From solar to wind energy to natural gas recovery, many of the technologies allowing us to transition toward a clean energy economy and creating entire new industries would not be possible without federal support. And the same is true for nuclear energy. This morning, we will listen to you all regarding the federal role in developing the next generation of nuclear energy technologies. I'm particularly pleased that as part of this discussion, we will learn more about innovative future fusion energy concepts that have the potential to accelerate the development and deployment of commercial fusion reactors dramatically. Fusion holds the promise of providing a practically limitless supply of clean energy to the world. In a sense, we're already dependent upon it because the energy that we get from that fusion reactor called the sun in the sky is essential to the existence of life on Earth. It's proving difficult for people to replicate what the stars are able to do through sheer gravity. But based upon several developments in recent years that we'll be hearing about in part today, I'm confident that we'll get there, and I hope far sooner than people may realize. In any event, I'm a strong supporter of fusion energy research, which is entirely different in terms of its impact and potential problems than fission. I believe that now is the time to build and operate experiments that are capable of demonstrating that man-made fusion systems can consistently produce far more energy than it takes to fuel them. I'm eager to learn about both the costs and the benefits of a wide range of new nuclear technologies, and I also look forward to hearing how nuclear energy can play an important role in developing a modern, clean energy economy. Again, I want to thank you all, our witnesses, for providing your insights today, and I look forward to hearing from the Chairman and working with the Chairman on nuclear energy issues moving forward. Thank you. I yield back the remainder of my time.
I thank the gentleman from Florida, and now recognize the gentleman from Texas, the Chairman of the full committee, Chairman Smith.
Thank you, Mr. Chairman. And today's hearing will examine opportunities for advances in nuclear fission and fusion energy technologies. We will hear from the Associate Laboratory Director at Argonne National Lab, the home of the world's first reactor to demonstrate a sustainable fission chain reaction. Argonne National Lab is responsible for foundational research and development in nuclear energy that has led to many operating reactors and reactor concepts that will be discussed today. These include the integral fast reactor and pyroprocessing. We will also hear from witnesses who represent private companies and a charitable organization, all of whom have invested in the development of advanced fission or fusion reactor designs. Nuclear energy provides reliable, zero-emission power. This technology represents one of the most promising areas for growth and innovation to increase economic prosperity and lower the cost of electricity over time. This will help keep the United States globally competitive. The Department of Energy's national laboratories provide vital opportunities for the private sector to invest in innovative energy technologies. This includes its open access user facilities, which are one-of-a-kind machines that allow researchers to investigate fundamental scientific questions. These facilities enable a wide array of researchers from academia, defense, and the private sector to develop new technologies without favoring one type of design. This represents a better approach than simply picking winners and losers through energy subsidies. DOE's labs also provide the fundamental research capabilities that lead to scientific publications or proprietary research. In this public-private partnership, private companies take on the risk for commercializing technology, while the government enables researchers to conduct specialized research that would not be possible without federal support. DOE's national labs keep America's best and brightest scientists working on groundbreaking research here in the United States instead of moving to research projects overseas. I am hopeful that today's hearing can demonstrate the importance of foundational research capabilities in the national labs that will lead to the next generation of nuclear energy technology. Inevitably, and I hope sooner rather than later, all Americans will benefit from this research.
The next witness is Mr. Nathan Gilliland, Chief Executive Officer of General Fusion. Before joining General Fusion, Mr. Gilliland served as an entrepreneur in residence with Kleiner, Perkins, Caulfield, and Byers, one of the world's largest venture capital firms. In addition, he was the president and co-founder of Harvest Power, a renewable energy company that turns organic waste into natural gas and electricity. Mr. Gilliland received his bachelor's degree in accounting from the University of California at Berkeley. Welcome, Mr. Gilliland. Mr. Gilliland, you're recognized.
Chairman Weber, Ranking Member Grayson, Chairman Smith, thank you very much for the opportunity to testify today about the emergence of new innovative fusion energy concepts and the importance of governmental support and working with U.S. labs. My name is Nathan Gilliland, Chief Executive Officer of General Fusion, one of the leading private fusion energy companies. I'll make 5 key points today and have done so in my written statement in more detail, which I'd like to submit to the record. First, as I would echo what Ranking Member Grayson said, the game-changing nature of fusion energy bears repeating. It's energy production that is safe, clean, and abundant. In a fusion reaction, 1 kilogram of hydrogen is equivalent to 10 million kilograms of coal. It's the energy density comment that you made earlier. Humanity would have abundant energy for millions of years. There's also no long-lived radioactive waste, no chance of meltdown in fusion reactions. The benefits to energy security can hardly be overstated. Second, U.S. support for magnetic fusion programs like ITER and inertial confinement programs like NIF have created an enormously beneficial source of research. ITER and NIF have justifiably been the highlights of the U.S. fusion energy framework and developed key insights into plasma behavior, material science, simulation codes, and many others. These programs should continue to be supported. Third, because of this historical research, innovation in alternative pathways to fusion have accelerated. These alternative approaches, both in private companies and in labs and universities, offer potentially faster and less expensive concepts. And demonstrable progress is being made, both in these labs, universities, and the private companies. Of particular note, work at Sandia, University of Washington, and Los Alamos are worth noting, as well as the three leading private companies, TriAlpha Energy, which is based in Southern California, Helion, which is based in Seattle, and ourselves, General Fusion. The progress of these alternative concepts was featured last summer in Science and Nature magazines. Novel fuels are being tested, new simulation tools developed, and we're all setting records of the stability of our plasma. So real progress is being made. Increased commercial viability, lower cost power, and faster progress are common threads in these alternative fusion concepts. Alternative approaches are reducing costs by applying existing industrial technologies to the challenge of fusion, primarily avoiding costly large lasers or costly superconducting magnets. Some have novel ways to protect the fusion reactor from neutrons. Others have simpler ways to convert heat into electricity. But of course, there are no silver bullets. These alternative approaches tend to be less researched and studied and are simply newer. The physics have not been fully explored. But we would argue the viability and efficacy of these alternative approaches can be demonstrated for less money. Some will show rapid progress and others will not. But dollar for dollar progress or failure can be demonstrated much more quickly. Fourth, though the majority of fusion research has been publicly funded, there is a place, and an important place, for private companies who can build on previous research and potentially innovate faster. The Human Genome Project is a great analog and a great example. The NIH built a core of research that was very strong, and from this, private industry was able to efficiently and rapidly innovate to sequence the genome. We see parallels in fusion energy. World-leading historical research is being done at labs and universities and has led to rapid innovation. And just like every energy industry, oil and gas, solar, wind, there will be multiple approaches that succeed in fusion. It's not a winner-take-all industry. Fifth and finally, going forward, we'd like to see more open innovation and information sharing across private industry, labs, and universities. For example, we all use computer simulation. It's a very important tool for us. We'd like to see co-development of simulation codes, more sharing of simulation codes. Another thing we'd like to see is greater emphasis on exchanges of physicists and PhDs across private industry and government labs. This leads to better sharing of historical research, current research, and the private sector would absolutely put resources into doing this. And labs and universities can help here at no cost to them. Ultimately, more cooperation between government-supported efforts and private industry can only accelerate progress. There is no value in silos. Let's push for more private-public partnerships, as Dr. Peters mentioned, and I'm sure Dr. Parmentola will as well. Let's push for more private-public partnerships to share data, build faster, and accelerate progress. The world needs fusion, and the faster the better. Thank you.
Mr. Gilliland, some of the problems associated with using fission for power generation are meltdowns, radioactive waste, and nuclear proliferation. There are other problems as well. Can you please elaborate in your testimony on why fusion may be able to avoid some of the problems associated with fission?
Yes, absolutely. Ultimately, it starts with the reaction itself. So fission is a large atom that can react spontaneously. Fusion is done with hydrogen only, and it's impossible for fusion to happen spontaneously. So it's a difficult reaction to get started, therefore very difficult or impossible for it to start on its own. So in a fusion reaction, there are the byproducts are helium and heat, or high energy neutrons. So there are not long-lived radioactive waste materials produced at all. Using hydrogen, certainly difficult to figure out how that could lead to proliferation challenges as well. So we do have normal safety challenges that any power plant would have. It's not that it's without risk completely, but certainly long-lived radioactive waste is not one of them.
All right, now your company is developing and advancing a unique fusion energy design that falls into a category of fusion energy concepts called magnetized target fusion. What is that?
Magnetized target fusion, I think it's worth stepping back for a second and describing kind of the mainstream long-standing fusion programs at a high level. ITER and magnetic fusion use a low-density plasma, much less dense than air, and hold it together with large superconducting magnets, and hold it together for long periods of time, even continuously. Laser fusion is sort of the other extreme, where a little fuel pellet is slammed with lasers in nanoseconds or picoseconds. The idea behind magnetized target fusion and other what we call middle ground fusion approaches is that those extremes are extremes. They're extremes makes them expensive. So big superconducting magnets cooled to 2 degrees Kelvin are expensive, as are using the world's largest lasers. It's not that those pathways aren't viable; they're just they appear to be expensive. So the middle ground uses density between the two and speeds of compression, speeds of shrinking that plasma that are much slower than laser fusion. So in our case, we compress a plasma called a spheromac plasma in about 80 microseconds, which is obviously much slower than the picoseconds or nanoseconds of laser fusion. So the idea is just simply put, it's to avoid the extremes and become much lower cost and ultimately more practical.
Now, my understanding is that your design has no permanent home in U.S. energy research, but is funded by a temporary ARPA-E program that you noted yourself in your testimony. Is there a value, in your opinion, to having such research permanently funded as a regular part of energy research by the federal government?
Sure. So I would comment, ARPA-E has done a great job on a fusion program. I think they're still in the middle of negotiating with the various recipients. So, whether or not we are a recipient of that, I don't know at this time. However, to your question, I think it's vital that the U.S. support this middle ground, and I think the primary reason is that a lot of significant progress can be made for small dollars. So some of these middle approaches are absolutely viable, some are not. We don't know which is which yet, but it will not take billions of dollars to determine that. So I think funding is one, but I think in my testimony I mentioned let's work together, labs and private companies, around simulation codes. Let's work together around exchange of PhDs and physicists. I think there's some simple things we can do to accelerate progress as well. But ultimately, I do obviously support this middle ground of fusion.
What's a rough time frame that you could provide, allowing for no undue optimism, for achieving net energy production?
It's a difficult question. There's no question about that. I think there's an interesting graph that plots Moore's law against fusion progress. So fusion progress being how much energy out of a reaction are we getting in, or how much are we getting out for what we're putting in, and it's actually quite interesting. They parallel each other. So I think the question is, we're nearly there. I think the large programs have determined that it can be done, and now it's a question of just how do we do it commercially, how do we do it economically? And I think that's the question, right? So I think there's 2 steps involved. One is building an alpha power plant or a prototype plant that demonstrates reliability, and then second, building commercial plants. So I'm spinning around your answer or your question a little bit, but we're certainly several years away. I would like to think that we as a set of alternative concepts can get there in the next 5 or 10 years, given the basket of options that are out there. I'm optimistic that within that basket, in that time frame, we'll get there.
My question is for Mr. Gilliland, and in your testimony, you're pretty forceful on the potential power of fusion energy. And for example, you write that the game-changing nature of fusion energy bears repeating. Energy production that is safe, clean, and abundant that would change the landscape of energy forever and greatly enhance energy security. At the 2 national laboratories that I represent, they do a lot of work in fusion energy. For example, at Lawrence Livermore, they have the National Ignition Facility, the largest inertial fusion facility in the world, which is an amazing research tool, which has produced a wealth of information, but its primary goal right now is to assist in the maintenance of the nuclear weapons stockpile. However, we have long-term hopes that it can be a sustainable energy source in the future. So keeping that in mind, and Representative Lofgren, who's on this committee as well, she has worked with me on supporting fusion. But keeping that in mind, do you think, Mr. Gilliland, that the federal government is spending enough to support fusion energy research? And if not, do you have a dollar amount in mind as to how much more we should spend? And would it be helpful to have an actually dedicated funding source for research into all different types of fusion, including inertial, for energy applications?
I would echo your comments on the National Ignition Facility and their leadership in the fusion energy space. You mentioned that their primary goal is around weapons. However, they're making huge steps in fusion energy as well. I think the number is they've improved by about 100 times their fusion yield in the last 3 years. So I certainly believe that continued support and even enhanced support of National Ignition Facility is warranted. Similarly, Sandia has an alternative approach called Z-pinch, which I won't get into the details of, but they've also demonstrated a huge amount of progress. So we're certainly supportive of all of the concepts of fusion, including magnetic fusion that General Atomics is quite involved in. I think where funding could, and make a big difference is in some of the alternative approaches. Most of the dollars go toward magnetic fusion or inertial confinement fusion, both of which have benefits and both of which have created really a base of research that everyone is benefiting from. I think the difference is that some of these middle ground concepts like ours and a number of others do have the potential to be faster and less expensive because of we don't need lasers or superconducting magnets. So I think it's a basket of alternatives and it should be approached that way. Each have their pros and cons across the spectrum. So I can't give you a dollar amount, but certainly support and enhanced support I think is absolutely warranted because the final point I'd make is whether it's fission or fusion or others, I mean, the world needs more energy, and energy is fundamental to the entire economy. So it's not one or the other; it's all.
Thank you. And also, with respect to Dr. Parmentola and Mr. Peters suggested that the federal government should develop a new nuclear reactor facility to test innovative reactor ideas. Now, knowing that we have few federal dollars allocated for this type of research, and it doesn't look like the trend is going up, it's actually going down. Do you have if you had to prioritize between fusion and nuclear reactors, any thoughts on that?
How to prioritize between fission and fusion? Is that your question? Again, I think they both have their pros and cons, right? I think fission certainly has the waste issue to deal with, proliferation and so forth, but there's certainly a number of viable pathways that fission has demonstrated with small modular reactors and so forth. So I think that it's a little bit of an apple and orange comparison. I think a demonstration facility could have both. I don't know why it couldn't have both. I think creating that regulatory framework is helpful for all of us. And again, I think it would be beneficial for us all to have it at one location.
I want to thank the witnesses for coming in today and for your testimony. It's been very, very informative, and we appreciate y'all being here with that. Our hearing's adjourned.